Let us now look into procedural assignments. Procedural assignments are used to assign values to registers. While the assign statement is used for combinational logic and assigning values to wires, procedural assignments are used to assign values to registers and can result in both combinational or sequential logic. They do involve data storage. As soon as you write inside of a register, there will be a data storage involved. And what does it mean? It means that the register will hold the value until the next procedural assignment to that variable. So we will keep this value until the next assignment is evaluated. And that occurs only within procedural blocks, which are either initial and always statements. Note that the initial statement is not supported for synthesis. Of course, the initial statement tells you, hey, at the very beginning, please consider this value. But at the beginning of what? Beginning of the minute? Beginning of the chip? Life? Beginning of the power-up? Beginning of time? We don't know. This is why the initial statement cannot be implemented for synthesis. It is used in simulation. In simulation it makes sense because that's the beginning of your simulation. And these always statements and any other procedural assignments are actually triggered when the flow of execution reaches them. What does that mean? Well, we need to look at what follows the always statement to understand when they are actually triggered. That is called the sensitivity list, and you might have multiple things. For example, if you have always with nothing after that, it is initialized, so it is evaluated only once during the first evaluation cycle, and that's it. However, when you have an always at and then an expression A or B or C, it means that whenever there is a change on A, B, or C, you will evaluate this block. And that results in combinational logic. For example, I will have a simple gate, an AND gate. You can describe by saying always at A or B, meaning that when A or B are changing, please compute Y is equal to A and B. All right? In addition to just combinational logic, you can use the keyword pos edge or neg edge. In that particular case, always at pos edge foo, pos edge, so the signal foo is going to be looked at, and as soon as we have a transition from low to high, we're going to evaluate the content. What does that mean? It means that every time the signal is rising from low to high, there is a rising edge, we will be evaluating something. It's basically sequential logic, where you will have a flip-flop or an edge-triggered flip-flop that will be reacting to the situation. The neg edge keyword is doing the exact opposite. It is reacting when the signal goes from high to low. So how do always statement work? Well, you will have the following syntax: always at sensitivity list, followed by the left-hand syntax equal to the expression. And that way, the at sensitivity will control when the left-hand statement, which can only be a register, will take the value coded by the expression. The expression can be a mix, again, of wires and register types mixed with operators. Let's go through an example of combinational logic first. So we have reg C, wire A and B. A and B are wires, scalar wires. C is a scalar register. You will have the always at A, comma B, which is basically A or B. C is equal to not A and B. In this particular case, the C value is going to take the not A and B, so it's a NAND gate, so it will be a NAND operation between A and B, only and only if A or B is changing. You can also have another keyword, always at star, C equal to not A and B. I like to point out the keyword star that basically tells you, hey, no matter what happens, if something moves, please evaluate this value. This is a very convenient option, but it is not the best practice when implementing your Verilog code. Indeed, you want to know exactly what is going on and what your finite state machine, or what your procedural assignment and future finite state machine you can build around it are going to react to. So I strongly not recommend the use of the store statement in your Verilog. In addition to this pure combinational, you can look at the storage operations, where we have the following keyword: reg q, wire clock. So q is a scalar register, clock is a scalar wire, and we have the always at pos edge clock, which means that every time there is a rising edge on the clock signal, I'm going to store the value d inside of the register q. While inside procedural statements, I can have conditional operations. You can use if statements with if expression, then do something, or if else operations. I'd like to point out that the else is always associated with the closest previous if that lacks an else. And you can use the begin end block to eventually make it more clear rather than just using the if and else. This is highly recommended for code visibility. However, in some cases where it is pretty obvious, you can look at the following example below. If index is larger than 0, and if reg A is larger than reg B, then result will be equal to reg A. Else, result will be equal to reg B. The else is related to the if reg A is larger than reg B expression, okay, because it is the closest that lacks an else. You can also create multi-way decisions where you have standard if, else, if statements, if expression, else, if, and so on and so forth. I would like us to review the blocking versus non-blocking procedural assignments. Inside of a procedural assignment, you're going to set registers to some expressions. And let's first review the blocking procedural assignment, where the left-hand statement is equal, with just the equal sign, to a timing control expression in that case. In this particular case, this must be executed before any assignment that follows. It is completely blocking the operation. It becomes sequential. I need to execute this operation before evaluating the next one. This is very different than the non-blocking procedural assignments, which is the left-hand statement arrow timing control expression that will be evaluated simultaneously when the block starts. That way, you will be able to control your operations differently and the behavior of your module differently. Be very much aware of that. It can be very useful, it can also be very tricky to make things right. So what does it mean to have actual blocking versus non-blocking statements? I like to look at the following examples, where we have assignment procedures, procedural assignments, and let's start from the top one. So every time we have a rising edge on the signal clock, we're going to go with a blocking statement A equal to Y and B equal to A. What does that mean? It means that the first operation I need to compute will be A equal to Y, which means that now A is equal to Y, containing the physical value of Y, and B is equal to A will follow, which is identical than having B equal to Y. So the resulting circuit will be having two flip-flops running in parallel and taking as the input the Y signal. Why? Because in the end, A and B will be equal to the Y value at the end of the procedural assignment. If we keep going with the examples, the second one, which is still blocking, will have B equal to A and A equal to Y. In that particular case, you will be able to first latch the value of A inside of B, and then latch the value of Y inside of A. And this results in the series flip-flops where Y will be the input A will be the intermediate signal and B will be the final signal. In that particular case, at every clock signal, the B value will take the previous value of A, and the next value of A will take the value of Y. This will be very similar than using non-blocking statement in this case. Indeed, if you're using non-blocking statements, A arrow Y and B arrow A, what does that mean? It means that when we evaluate the behavior of these procedural assignments, you are going to evaluate them both at the same time. So A, the next value of A will take the current value of Y, while the next value of B will take the current value of A. So that all results in having this cascading behavior. Now, it is important to note that different circuit structure, as we just saw in the previous slide, will result from different types of procedural assignments. Therefore, you cannot mix assignment types in the same always block. And in this context, a non-blocking assignment is often a better model for hardware, because indeed real hardware is and should be concurrent. So you don't want to transform your piece of hardware into just a magnified software operation. You want to use the complete power of parallel optimization on your hardware system. And however, blocking will often be better for setting subset of signals. You want to set them to default at the beginning and then reset only the ones that change over the course of the system.